Hey there, science fans! Have you ever baked a cake and it didn't turn out quite right? Maybe it was a little too dry or a little too sweet. In science, we conduct experiments to understand the world around us. Just like baking a cake, experiments rely on measurements. And just like your cake, those measurements might not always be perfect. This is where experimental error comes in. It's the difference between the measured value and the true value. Understanding and managing experimental error is crucial for obtaining reliable and meaningful results in any scientific investigation. Imagine you're measuring the length of a leaf. Your ruler might be slightly off, or you might not be holding it perfectly straight. These small discrepancies contribute to experimental error. By acknowledging that errors exist and learning how to minimize and account for them, we can improve the accuracy and reliability of our scientific findings. So, let's dive into the world of experimental error and discover how to become better scientists. Imagine you're measuring a piece of string. You find it somewhere between 25 and 26 centimeters long. Your ruler only has markings for centimeters, so you estimate the extra bit to be about 0.3 centimeters. You report your measurement as 25.3 centimeters. The digits 2, 5, and 3 in your measurement are all considered significant figures. They tell us something meaningful about the precision of your measurement. Significant figures indicate the confidence we have in a measurement. The more significant figures, the more precise the measurement. There are specific rules for determining which digits are significant. For example, all non-zero digits are significant, as are zeros between non-zero digits. Understanding significant figures is crucial for performing calculations with measurements. When multiplying or dividing, the answer should have the same number of significant figures as the measurement with the fewest significant figures. This ensures that we don't overstate the precision of our results. In the world of measurements, errors aren't created equal. We can classify them into three main types: systematic, random, and gross errors. Each type has its own characteristics and impacts our results differently. Systematic errors, like a wonky scale that always reads a few grams too high, consistently shift our measurements in one direction. These errors can stem from flawed instruments or procedures. Random errors, on the other hand, are like unpredictable gusts of wind affecting our measurements in unpredictable ways. They arise from factors beyond our control, causing measurements to fluctuate randomly around the true value. Gross errors are the blunders of the measurement world, often caused by human mistakes or instrument malfunctions. Imagine accidentally recording a measurement as 100 centimeters instead of 10 centimeters. Understanding the different types of errors helps us identify their sources and minimize their impact on our experimental results. By carefully controlling our experimental conditions and using appropriate techniques, we can mitigate the influence of these errors. Imagine you're trying to hit a bullseye with a bow and arrow, but your arrows consistently land to the left. This suggests a systematic error in your aim. To correct this, you need to adjust your aim to the right. Similarly, in science, we can often correct for systematic errors once we've identified their source. For example, if we know a particular thermometer always reads 2 degrees Celsius too high, we can simply subtract 2 degrees Celsius from all our readings to obtain more accurate values. Sometimes we can calibrate our instruments using known standards to minimize systematic errors. Calibration ensures that our instruments are providing accurate readings. For instance, we can calibrate a scale using a set of standard weights to ensure its accuracy. By implementing appropriate correction techniques, we can improve the accuracy of our measurements and reduce the impact of systematic errors on our experimental outcomes. Remember, a stitch in time saves 9, and addressing systematic errors early on can save us from drawing inaccurate conclusions later. Precision versus accuracy. Two sides of the measurement coin. Imagine you're playing darts with a friend. You both throw 3 darts, aiming for the bullseye. Your friend's darts land close together, but far from the center. Your darts are more spread out, but closer to the bullseye on average. Your friend's throws are more precise, meaning they are closely clustered together. Your throws, however, are more accurate, meaning they are closer to the true target, the bullseye. For any of you readers watching, take the Hunger Games, for example. Notice how Katniss's darts are accurate and precise. Peeta's darts are precise but not accurate. Gale's darts are accurate but not precise. And Haymitch is neither precise nor accurate. In science, precision and accuracy are two essential concepts related to measurements. Precision refers to the closeness of repeated measurements to each other, while accuracy refers to the closeness of a measurement to the true value. High precision indicates that our measurements are repeatable and consistent, while high accuracy indicates that our measurements are close to the actual value. Both are important considerations for obtaining reliable and meaningful results in our scientific endeavors. Are you enjoying the video so far? Consider liking and subscribing so you can ace that chemistry class. Now that that's out of the way, let's get back to the video. Absolute versus relative uncertainty, quantifying the doubt. In the realm of measurements, uncertainty reigns supreme. No matter how careful we are, there will always be some degree of uncertainty associated with our measurements. To quantify this uncertainty, we use two main types: absolute uncertainty and relative uncertainty. Absolute uncertainty is the margin of error associated with a measurement, expressed in the same units as the measurement itself. For example, if we measure the length of a pencil as 15.0 centimeters with an absolute uncertainty of 0.5 centimeters, it means the true length likely falls between 14.5 centimeters and 15.5 centimeters. Relative uncertainty, on the other hand, expresses the uncertainty as a percentage of the measurement. It provides a measure of how large the uncertainty is relative to the measurement itself. In our pencil example, the relative uncertainty would be 0.5 centimeters divided by 15.0 centimeters, multiplied by 100%, which equals 3.33%. Understanding both absolute and relative uncertainty is crucial for interpreting the reliability of our measurements and for comparing different measurements with varying uncertainties. It helps us appreciate the limitations of our measurements and avoid drawing overly precise conclusions. Propagating uncertainty, a mathematical balancing act. Imagine you're building a tower of blocks, and each block has a slight wobble. As you stack more blocks, the wobble of the tower increases, reflecting the combined uncertainty of each individual block. Similarly, when we perform calculations with measurements that have uncertainties, we need to propagate those uncertainties through the calculation. This means accounting for how the uncertainties in each measurement contribute to the overall uncertainty in the final result. The rules for propagating uncertainty depend on the mathematical operation being performed. For addition and subtraction, we add the absolute uncertainties. For multiplication and division, we add the relative uncertainties. For example, if we add two lengths, 10.0 plus or minus 0.5 centimeters, and 5.0 plus or minus 0.3 centimeters, the sum would be 15.0 plus or minus 0.8 centimeters. Propagating uncertainty ensures that the uncertainty in our final result accurately reflects the combined uncertainties of the measurements used in the calculation, providing a more realistic estimate of the reliability of our results. Mastering uncertainty, the cornerstone of reliable results. In the world of science, uncertainty is not our adversary, but rather a constant companion. It's an inherent part of the measurement process, and by embracing and managing it effectively, we can strengthen the reliability of our scientific findings. By understanding the concepts of significant figures, different types of errors, precision and accuracy, and uncertainty propagation, we can make informed decisions about our experimental design, data analysis, and interpretation of results. Mastering uncertainty allows us to present our scientific findings with appropriate levels of confidence and communicate the limitations of our measurements transparently. Remember, science is a process of continuous refinement, and by acknowledging and addressing uncertainty, we pave the way for more robust and reliable scientific discoveries. Conclusion: embracing the uncertainty in science. As we've journeyed through the world of experimental error, from significant figures to uncertainty propagation, we've gained a deeper appreciation for the inherent uncertainty in scientific measurements. Uncertainty is not a sign of weakness, but rather a testament to the complexity of the natural world and the limitations of our instruments. Instead of fearing uncertainty, we should embrace it as an integral part of the scientific process. By understanding the sources of error, quantifying uncertainty, and propagating it through our calculations, we can minimize its impact on our results and enhance the reliability of our scientific conclusions. Remember, science is not about finding perfect answers, but rather about asking increasingly refined questions and seeking the most accurate representation of reality. even if it comes with a margin of uncertainty. So, let's embrace the uncertainty, for it is in the face of uncertainty that science truly flourishes. Like and subscribe. Make sure to share if you found this useful. Be sure to have a nice night, and good night.